Welcome back everyone. In this lecture actually I will prove Lee's theorem and then we will see some of the consequences of Lee's theorem. Okay. So, in the last lecture we saw Engel's theorem. So, Engel's theorem actually provided a structure result about the nilpotent Lie algebras. So, very similar to that Lee's theorem will actually provide some structural results about solvable Lie algebras. Okay. So, here is the theorem. So, again this is actually a easy consequence of invariance lemma. Okay, you start with a linear Lie subalgebra, let us call it G. So, let G being linear Lie subalgebra. As before, we always assume V is non-zero and finite dimensional vector space over C. Okay. So, then what we want to say, so here is the theorem. So, if G is solvable, okay, so then we can actually get a basis. So, there exists a basis B of V such that, so in which every element of this Lie algebra is represented by an upper triangular matrix. So, in the case of nilpotent Lie algebras, so we got strictly upper triangular matrices, but in the case of solvable Lie algebras we get upper triangular matrices. So, there exists a basis B of V in which every element of G is represented by an upper triangular matrix. So, we already know that any subalgebra of this Lie algebra of upper triangular matrices, so that will be solvable. So, indeed Lee's theorem gives us converse of that statement. Okay. So, let us see how one actually proves this. So, this is also again one can actually think as so whatever result that you have learned in linear algebra. Okay. So, that is about given one matrix you can have what is called this Jordan canonical form, which looks like upper triangular matrix. Okay. But now we are actually dealing with family of linear transformations, but if you look at the Lie algebra structure on that is actually solvable Lie algebra structure. So, if we have that solvable Lie algebra structure, then we can assure that there exists a basis such that every element of that solvable Lie algebra is represented by an upper triangular matrix. Okay. So, let us see how to prove this. Again this theorem will be a consequence of the following proportion. Okay. So, as we actually did it in the nilpotent algebra case. So, once we establish this proportion, the theorem will follow immediately from the induction on the dimension of V. So, that part I will leave it as exercise. So, I will only do this proportion. So, you have this G as before sitting inside GL of V, where V is a non-zero complex vector space. So, then what we can prove that there exists some vector V which is non-zero vector in capital V such that this V will be eigenvector for simultaneous eigenvector for all x in G. So, what does it mean? So, it means, so if you look at this vector and then the G action on that vector. Okay. So, there exists non-zero vector V in capital V such that, so you take x times V. Okay. So, this is actually just inside this one dimensional space spanned by V for all x in G. So, this is same as saying that, so this is actually a eigenvector for all x in G. So, it is not hard to see. So, using this information, okay, so given x in G, so this x v will be some scalar times v, okay, which we can call it lambda x. So, this association x goes to lambda x. So, this will define a map from G to complex numbers. So, this map one can check, okay, I will leave it to you to check, is a linear map, okay, that is easy because G is actually a linear space. So, check this lambda is a linear homomorphism. In particularly lambda is a weight for this G. Okay. So, let us actually see why this is actually true. So, here is the proof. So, as before we will actually establish an ideal inside your Lie algebra G, which is of codimension 1. So, since G is solvable, so we must have the derived algebra GG properly contained in G. Okay. So, now you can take A be a space containing GG, okay, and of codimension 1. So, the dimension of A is dimension G minus 1. Okay. So, then it is immediate that A must be ideal inside G, and choose y is in is not in capital A. So, then this G will be equal to A plus C y. Okay. So, this is all like the argument that we gave before. So, very similar to that we have this. So, now so for this, like it looks like the dimension of G must be at least 2. So, if dimension of G is 1, then there is nothing to prove. So, it is just a result from the linear algebra. So, you can assume the dimension of G is at least 2. Okay. So, now we got this capital A, which is an ideal of codimension 1. So, now using the induction, we can see that so there exists a non-zero weight space or weight for this capital A such that the corresponding weight space is non-zero. So, since A is being ideal of G, A is also solvable. So, that implies there exists lambda in A star such that this V lambda which is non-zero. So, that is those vector in V such that A V is lambda A V for all A in capital A. Okay. So, now if you recall what is invariance lemma, so that simply says that this V lambda is G invariant. Okay. So, this is just using the invariance lemma. So, now we have V lambda is G invariant, that means this y will act on V lambda. So, since y is a linear transformation acting on V lambda and we are working over complex numbers which is algebraically closed. So, that implies we have a eigenvector for this y. Okay. So, there exists some w inside this V lambda such that this y w will be exactly equal to some mu times w, okay, for some mu which is eigenvalue of y complex number. So, now it is easy to see that we can extend this lambda to G such that lambda of y to be this mu, and using this lambda we can see that this W is actually eigenvector for all of them. So, okay, this is lambda of x W for all x in G. Okay. So, that is what we wanted to actually produce. So, that is we succeeded. So, now as before what one can do, we can take that vector, okay, C W. So, you call that is subspace U. So, this is actually G invariant subspace. So, then what you can do, you can go modulo that U. So, then naturally G will act on this, okay, or you can actually look at the image of G inside this GL of V modulo U. Okay. For each x in G will induce x bar, which will be a map from V modulo U to V modulo U. So, now look at this x bar where x is coming from G. So, this will be a subalgebra of this GL of V modulo U. So, now this dimension is actually strictly less than the dimension of V. So, by induction what you can say that there is a basis of this V modulo U. With respect to that basis, all the elements of this G dash represented as upper triangular matrix. So, since G dash is actually solvable as being quotient of this G, okay, I will leave it to you to check G dash is indeed solvable, okay, that is not hard to actually check. So, once you check that this correspondence x goes to x bar is actually a Lie algebra homomorphism. So, that would imply that G dash is solvable. So, now by using induction you get a basis of V mod U. With respect to that basis, each element of G dash represented upper triangular matrix. Now, if you take that basis of V mod U and then add this element W with that. So, then you get a basis of capital V. So, then it is not hard to prove with respect to that basis each element of x will be represented as upper triangular matrix. So, I will leave you to check all those things, okay. Check that, okay, here there exists a basis B of V mod U such that x bar B is upper triangular matrix. So, now you can take B union the W. So, that will be a basis of V, and if you call this is B dash, then x B dash is upper triangular for all x in G. So, this is something I will leave it to you to check. Okay. So, that proves that proves the least theorem. Okay. So, G is solvable if and only if, okay, you assume that G is coming from GL of V, then there exists a basis such that this is happening. Actually, like one can say that this is true even for any arbitrary algebra as before, because if you start with an arbitrary algebra, then G modulo the center G. So, you can say that that is embedded inside GL of G. So, if G is solvable, then this G modulo center G will be solvable. So, there will be a basis in which all elements of this add G will be represented as upper triangular matrix. So, in particularly you can see that all the images of G also will be represented as upper triangular matrices. Okay. So, actually the generalization of Lie's theorem is not true over general fields. Okay. So, because the invariance lemma is used very crucially. So, if you recall the proof of the invariance lemma, so we actually had some situation like this. So, the trace of x y times m being 0 implied that. So, this m being the dimension, okay, some dimension of some subspace. So, then from this we concluded that the trace of bracket x y is 0. Okay. So, if you work with the characteristic P field, then this conclusion is not true anymore. Okay. So, that is why this Lee's theorem is not in general true. So, what I mean by Lee's theorem, that there exists a basis in which each element of your Lie algebra is represented as upper triangular matrix. Okay. So, for example, what you can do, you can take P to be a prime number, and then you can work with for example, F p or any field F with which has characteristic P. Okay. So, then look at this particular two dimensional subalgebra of GLPF. Okay. Take this G, which is span of x y inside GL of F p 2. Okay. So, I guess I used the other way notation. So, this is GL 2 F p, 2 by 2 matrices where entries are coming from F p. So, I will tell you explicitly what is this x and y. So, you take x to be this particular matrix where diagonal entries are 0 and this southeast corner is 1, okay, and the first off diagonal entries are 1 and all other entries are 0. Okay. So, this is your x, and what is y? So, y you take it to be the diagonal matrix where diagonal entries are 0, 1, 2 etcetera p minus 1, all other entries are 0, and it is not hard to check. I will leave it as exercise. So, it is not hard to check that the bracket x y is actually indeed x. In particularly, G is a two dimensional subalgebra of this GL 2 F p. So, now if you think about it, it is actually solvable. Okay. So, this is solvable Lie algebra. So, that is easy to see because the derived algebra is one dimensional. If you take G of bracket 2, that will be 0. Okay. But it is easy to show that x and y, they will never have some common eigenvectors. Okay. So, it is easy to prove that x and y have no common vector, common eigenvector, because Lee's theorem says actually over complex numbers any solvable Lie algebra will have common eigenvector. Okay. But here we have established two dimensional example over F p that does not have any common. So, again I urge you to check these facts. So, these are all not very difficult facts to prove. Okay. So, in particularly, so the conclusion of Lee's theorem fails over characteristic P fields. Okay. So, it is a very interesting example, that is why I just wanted to state it here. Okay. Now, what we will do actually using Lee's theorem, we will actually give one more characterization of this nilpotent Lie algebras. Okay. So, you can easily see that so any from Engel's theorem, any nilpotent Lie algebra like if it is okay, let us say linear Lie algebra. Okay. So, that can be embedded inside strictly upper triangular matrices. Okay. So, now that means okay, if you think about using the Lee's theorem, if you start with solvable linear Lie algebra, so then there is a basis such that all elements of this Lie algebra can be represented as upper triangular matrices. But if you take derived algebra of upper triangular matrix, that will be strictly upper triangular matrix. So, that indeed proves if you take G, which is solvable linear Lie algebra. So, then the derived algebra must be nilpotent. Okay. So, this is something very interesting consequence of Engel's theorem. So, this is actually somewhat characterize all solvable Lie algebras. Okay. So, here is the theorem, it is actually easy consequence of Lie's theorem. So, if you take G, so this is solvable if and only if the derived algebra is nilpotent. Okay. So, if G is solvable, so then we can easily see that okay, at least for linear Lie algebra it is very clear. Okay. Maybe I will leave it to you to think about what happens for the arbitrary Lie algebra, but for linear Lie algebra what happens, if G is solvable, there exists a basis such that G can be realized as inside some T n C. So, that will imply that the bracket G G is inside the strictly upper triangular matrices. So, that implies that this G G is nilpotent. Suppose the derived algebra is nilpotent, then what happens? Obviously, the derived algebra is solvable. Okay, nilpotent implies solvable, but if you take the quotient G modulo the derived algebra, so since it is abelian, so that will imply that G must be solvable, because the derived algebra is solvable, the quotient is solvable, so G must be solvable. So, this way is obvious. Okay. So, only the other way uses Lie's theorem. So, like I said, you think about general arbitrary Lie algebra, whether this satisfies the same characterization. Okay, I will stop here with this characterization. So, in the next class I will actually continue with the representation theory. Okay. Thank you very much.